Okay, this is for Cliff and anyone else who thinks they might need it for studying. Leah also was not here, so this could be for Leah. Special for you guys. Please, would you like the video for me? Maybe make a comment if it helped you a little bit. So this is our note for lesson 5, right? And we are going to talk about dependent events and independent events, okay? So with dependent events, there's something called conditional probability. And for conditional probability, we need to first we need to talk about independent events, if two events are occurring together, or dependent events, okay? And so you look at it like this. The formula for independent, things are independent if the probability of both of them happening is equal to the multiplication of the separate probabilities of each event. Okay? If those two things are equal, then you say that they are independent events. Okay? But if you have the probability of both of those things happening together equal to something just a little bit different, again, the A times, not the B, but a restricted version of the B, probability that B happens given that A is already true or has already happened. That sounds kind of weird. Let me show you how that's going to look in just a second. This is called the conditional probability of B happening if A already happened, or if A is already true. Okay? So we're not talking about the whole sample space anymore. What does that mean? Okay? Well, conditional probability, that's the one with this thing right here. This conditional probability, okay, is the probability that one event will happen if it is known that the other event has already happened. We just said that. We can rearrange the multiplication rule. Forget about that. We don't need that. But what we do need is the these three here. Okay? So what does this formula mean for probability of A? We can actually make it there. Probability of A is equal to, if we rearrange the formula, probability A and B over the probability of A. Okay? I would say this one should be, probability of B given A. Okay, so it looks like that. What does it mean? It's a lot easier to see what it looks like and what it means. So if we know that A has already happened, then we don't care about anything out here or in here, because that's only in B. If we know that we're only talking about A to begin with, and that's our full sample space, all of that, like our bottom of the fraction, you can see that you have in the bottom of the fraction here, you have the A. So you're just talking about the A circle. Then, if B is going to happen, it's going to happen inside of the A. So it's going to be in here. Okay? The B part that is in the A. So what does it mean here? Okay? The formula for probability of B given that A has already happened, given that we're restricted to just the A circle, is the probability of A intersection B over, this is a fraction bar, the probability of A. Okay? So that's what we had up above. Now, Here we have hair color and eye color in the columns, all right? We have a total of, our totals are on the bottom, okay? All over here. And we select a woman, problem number A, find that she has brown hair, okay? If we pick somebody with brown hair, then what is the probability that she will also have hazel-colored eyes? Okay, so let's look at the brown hair. I'll do a different color. The brown-haired people are right here. If we pick somebody from the brown-haired population, okay, how many, what is the probability that she will also have hazel eyes? Eye color hazel, right here, right? So where's the intersection? Because what we need is probability, I'm trying here, of hazel eyes given that we're talking about only the brown-haired people is equal to the probability of both of those things, which is here, because it's the intersection of both of them, over just the brown hair people. So what's the brown hair total? 143. Probability of brown hair. Okay, so that means we have 143 on the bottom because that's the brown haired people total. Okay, and we have a 29 on the top because that's your brown, that's your both, that's the intersection. Technically, you should have 29 over 313 over 143 over 313. But the 313s are going to cancel out. So you end up with just that, which is point what? 203. You should try it out, make sure on your calculator. Selecting woman, she has, what's the probability of selecting a woman if she, and find she, if we select a woman and find that she has brown eyes, what is the probability that she also has black hair? So, brown eyes, black hair. Probability, brown eyes. Actually, black hair. Given that she has brown eyes. Okay? That's equal to probability of both over just the brown eyes. Probability of brown eyes. Probability of brown eyes, we already know, is 143. Probability of both in this case. Oh, no, wait a minute. Brown eyes? 143 or 122? Yeah, 122 brown eyes. My bad. 122 on this one. 22, okay. And probability of both brown eyes and black hair. We can sort of lighten this up. Probability of brown eyes and, I'll get rid of this, it won't go away, will it? There we go. Brown eyes and black hair. Brown eyes, black hair. Our intersection is 36. So we have 36 on top. And that's going to give us 0.295. Yay. Okay. So the trick here with the cards is if you're replacing the card in the deck or not. If you are replacing the card in the deck, then everything is independent. The second pick of the card doesn't depend anything on how many cards are in the deck from the first one. But on the other hand, it's dependent. It's dependent if you are not replacing the first card before you pick the second card out of the deck. Okay. And again, in the real world, it's kind of hard to tell. So you use this. A intersection B. Is it independent? Does the probability of A times the probability of B equal the intersection, the probability of both of them happening? And we have produce and frozen and fresh. Are they independent? We need to do the independent test, which is this one. To see if they're independent, you have to try that. So blueberries and fresh. Blueberries and fresh. So 20. And we could put the fractions on the bottom. We will, out of 140, because that's the total for all the fruits. And fresh, so we've got the intersection of the two, and we ask, is it equal to just the probability of blueberries times the probability of fresh? Probability of being a blueberry, 56 out of 140, times the probability of being a fresh thing, 50 out of 140. And so we do the left and do the right, and I think if you get 143 exactly on both sides, okay, I think that they're equal, so you would say yes, they are independent of each other. That's the independence test. Stop the video and try yourself. We're doing the test to see if they're equal. Probability of avocado times probability of frozen. Right? Probability of avocado and frozen is 15, I think, over 15 over the total, 140. Is it equal? Put a question mark. Probability of avocado, 9. No, wait a minute. How many avocados are there? 24. 140 times. And frozen is 90 out of 140. Okay, so we need to multiply those together. If you do it right, you should find out that they're pretty close. They won't be so close on the test to mess you up. That's that one, and over here we get 0.11. So they're not equal. So no, they're not independent.